Good afternoon, everyone, and thank you for attending our Industrial Heat Trace webinar. My name is Ryan Wood, Content Marketing Manager here at Liberty Electric Products. Before we get started, just want to let you all know that you'll be muted during the presentation, and we will not be doing a live Q&A. If you do have any questions as we move along, please enter them into the questions panel located in the webinar control panel, and we'll be sure to reply back to you by email. Also, we will be recording this webinar and we'll post both the recording and the slide deck on our website and YouTube channel. Our presenter today is Rob Zerillo. Rob has been in the industrial commercial heating business for over 16 years, first working with the Cleaver Brooks distributor and then for the last 12 years with Liberty Electric Products with a focus on electric heating applications. Rob has worked on and developed solutions for more than 500 different heat trace applications in upstate New York. His primary responsibility is being in the field at job sites, working with engineers and architects on new designs, and helping contractors with installations. So, without further ado, I'll pass it over to Rob.
Thank you very much, Ryan. I appreciate it, and I appreciate everybody else here spending some time with us on a beautiful upstate New York Friday afternoon. So we will try to keep the content of this presentation, right to the hour limit, and get you folks out of here, okay? So without further ado, let's get into our slideshow. So for our agenda today, we're going to cover 4 different segments here. Mainly, we're going to talk a little bit about the heat trace cables themselves. We're going to spend a little bit of time to familiarize you with the most predominant heat trace cables that we see for this application. We're going to talk a little bit about the industrial applications that we run into the most, which is typically process temperature maintenance and freeze protection. We're going to spend a little time on controls. This is a segment that we could literally develop our course around this one itself, but we will familiarize you with just the most popular control configurations that you'll typically see, and then kind of finish with some tips on system designing, and some installation tips put into that same section as well. So to get into the different types of heat trace cable itself. All right, so heating cables, for anybody new to this presentation or to this product line, a heating cable is basically an extremely versatile heating element that can be used for several different applications, and they're primarily in this industrial segment used for, again, temperature maintenance in pipes and for freeze protection. So when we talk about temperature maintenance, that really refers to ensuring the fact that the fluid traveling inside of that pipe does not lose its temperature from point A to point B. Okay, what we're trying to do is ensure that whatever's inside of that pipe is going to remain at its process temperature from start to finish. When we talk about freeze protection, again, it doesn't always have to be water. We know water freezes at 32F. Greases, syrups, different fluids with higher viscosities that are thicker can generally freeze or congeal at higher temperatures. So, when we talk about freeze protection, it doesn't always mean water, but yeah, most of the time it is. Okay. All right. The heat trace cable, this is a common thought process that's out there, to folks that don't work with this material as regularly as we do. But the heat trace cable itself doesn't actually add heat to the process, or it certainly isn't intended to. It's really just there to offset your losses off the skin of the pipe. Okay. When we calculate these heat losses, there are some factors that go into it. It's going to be different based, on what's the temperature that you're looking to maintain inside the pipe. And then, of course, what's the pipe material, how big's the diameter, and how much surface area does it have that's emitting heat off of it. And of course, how much insulation we're going to put around it as well. That's another thing that is extremely critical, because heat trace cable really cannot work effectively without its partner insulation. So when we talk about heat losses off of the skin, we do this in terms of watt per foot, okay? And as we get into each of these heat cables, you're going to see that they have values, wattage values per foot of their heat output. So this will all make sense in a few more slides here, but basically when we talk about each of these cables is going to have a specific function, and there's advantages and disadvantages, you could say, to each. So, you know, basically to reiterate what we just mentioned a moment ago on that previous slide is that, you know, heat trace cable is basically useless without insulation to cover it and hold that heat into the skin of the pipe. I mean, if you could imagine, you know, just looking at this picture here to the right, if we had these heat cables working on a 30-degree day, they're emitting literally 95% of their heat to the ambient air. So again, it's not doing you much good for whatever's inside the pipe, okay? So again, insulation goes hand in hand with your heat trace cable. All right, so 3 main types of heating cables: self-regulating heat cable, constant wattage, and then mineral insulated cables. Self-regulating cables are really by far going to be your most popular. These cables have a variable wattage output. They're very versatile. They're easy to work with, and we're going to get into how they actually get their name of self-regulating in a moment. Constant wattage cables are, again, they can be very easy to work with as well. You know, easy to splice, terminate out in the field. You know, but they've got some different properties to them that we're going to identify in addition to, say, self-regulating. And, you know, basically the mineral insulated cables are also very much similar to a constant wattage cable and how they function. Okay, these are engineered and produced specifically per application, so they're a little bit more complex than your standard constant wattage, and we'll get into that here in a moment. All right, so self-regulating cables. Low temp self-reg cable is what you're going to see predominantly in a lot of these scenarios because of the fact it's so versatile. This cable has a great temperature range that it can work within, and basically it's the most energy efficient. There's no question it's the most energy efficient. But, you know, because it's the one cable that can actually touch against itself without destroying itself, that alone makes it the most popular cable choice, okay? You know, basically how this cable works is through expansion and contraction based off of the temperature of whatever it is up against, okay? All heat cable manufacturers are consistent in how they rate the value of their cables, okay? It's an industry standard that when we tell you it's a 3, 5, 10, 12 watt a foot cable, that's what it puts out at 50 degrees F. And the colder that surface temperature gets that it's up against, the more heat output the cable is going to deliver. Conversely, the warmer the cable gets, the less heat it's going to want to put out, okay? But we're going to talk a little bit about some of those limitations here in just a second as well. So some of the things that help determine its output is the content of irradiated carbon. That's the core of this cable that basically has the material in it that allows it to expand and contract. So as you can imagine, if you have higher content of that material in the cable, you know, proportionately your temperature increases should be able to go higher, you know, et cetera, et cetera. So these cables typically in the low temp form, this is also pretty standard across the industry, is that most of these cables will operate up to about 150 F, and they will begin to destroy themselves around 180. So based on those temperatures alone, you know, this, you can kind of put it together with something like, say, PVC or plastic-based piping. You know, this becomes a very safe alternative to use with them. And of course, you know, lastly, this is a cable that is rated for class 1, Div 1, Div 2 applications as well. You know, it's a fully sealed unit. So again, the terminations and the fittings that we would put with it would make this compliant with any class 1, Div 1, Div 2 applications. So there's a couple different types of self-regulating cable. We've got obviously low temp, which is going to be, I think, bar none, the lion's share of the applications out there. But medium temp is basically the exact same product. It's just rated for higher tolerances. This particular cable and medium temp self-regs are definitely of an industrial grade intent and purpose. These things can basically handle up to 300 F outputs. They can handle up to about 420 feet, or I'm sorry, 420 degrees of maximum exposure temperature. So this product, you know, because of its higher tolerances for heat, This is a product that we would strongly recommend to not put on plastic or PVC-based systems. So, you know, again, you can kind of start seeing a little bit of the separation between what low and medium temp is good for. Okay. Process temp, you know, again, a little bit more limited, you know, in terms of its applications. But, you know, what this really comes down to is that depending on what your process temperature is, we want to make sure that we're giving you the right product with the properties and the jacketing and its temperature output to ensure success in your application. All right. So when we look at how a self-regulating cable is constructed, as you can see, you've got these two parallel 16 gauge bus wires. Okay, it looks a lot like a piece of Romex cable. And then that second layer, I apologize, this is a black and white type picture, but that irradiated carbon matrix, it looks like black licorice, basically binding those two bus wires together. And that's really where all the magic happens in the cable. That's where your expansion and contraction is going on. And then you've got a primary over jacket, a tin copper over braid for protection and grounding purposes. When you twist up this tin copper over braid, you go to terminate it. That actually becomes your ground braid. And then, of course, your outer jacket is going to be, in the case of an industrial application, much more like a chemical resistant Teflon jacketing for corrosion resistance. All right. So when we talk about, you know, again, the nature of these cables, you know, how they, oh, I'm sorry, I went backwards too, so I apologize for that. Let me move forward here. So when we talk about that expansion and contraction, all right, this cable works off of the temperature of the surface that it is up against. So if you can imagine, you know, just taking a strip of energized heat cable and putting it against a block of ice, as things do when you freeze them, they want to constrict. They want to, you know, basically shrink. So as it does that, that black carbon mastic pulls those two bus wires a little closer together. Okay, it's nothing you're going to see really with the naked eye, but as it pulls those two bus wires a little closer together and that mastic constricts, it opens up more resistance or electroconductive pathways that ramp your cable output up. And conversely, if you put this cable against, say, a pipe temperature of, you know, 120 degrees, let's say, as things do when you heat them up, they want to expand. And in doing so, that carbon mastic wants to push the two bus wires further away from each other. And that's what throttles your cable back or reduces the wattage or heat output. Now, it's important, you know, even in this graphic here where you see that blue primary jacket, is that the primary jacket wrapped around that black carbon core does not allow it to expand out very far. So it's important to note that whatever the rated duty of that self-regulating cable is, if it is a 5 watt a foot cable, okay, and you put that against a 100-degree surface, for example, is that you're really not going to go much below 5 watts a foot. You know, maybe you get down into 4, 3.8, but it's never going to reduce down to, like, say 1 or 2 watts per foot, because the primary jacket of the cable is not allowing it to physically expand out any further. Okay. All right. Now, here's probably the most confusing part about self-regulating cables is when we talk about the circuit length. Okay. Because these are self-regulating and they have a variance of wattage from, call it low to high, or let's just say rated duty to high even, sizing your circuits can become confusing at times because of the fact that, you know, again, they're not always going to have a consistent wattage output. So what we have to do is take what the maximum wattage potential of the cable is and size your circuit according to that. Okay, so we typically design with 30 amp 2-pole breakers to feed our heat trace circuits. So in that particular scenario, all right, a 5 watt a foot cable has the potential to pull a maximum of 12 watts a foot on that cable due to its construction. Now, the only time that should ever happen is either if that thing was fully encased in a block of ice, okay, which is obviously chances are slim to none. But the other time that it happens is during startup inrush current. So that's what we're worried about in most cases, and why we have to size these circuits accordingly to make sure that when there's a contact closure and you send power to your cable, that you get that millisecond spike where it might jump to 12 watts a foot, and we don't want that to nuisance trip your GFI rated controls, okay? Because whether you do your GFI at the breaker or whether you do it within the control panels and controls that you're gonna see in some slides a little later here, you know, either way, it's a 30 milliamp GFI code requirement that has to be on that circuit, okay? So basically all we're doing is ensuring the fact that we can't put too much cable on that circuit and just get nuisance trips every time it wants to kick on. So if you look on the left side of this page, based on a 30 amp 2-pole breaker and a 5 watt a foot cable, this gives you a pretty good idea right here about how far you can run per circuit length based on the voltages. Now, as long as we're talking about voltages, one thing to note here too is that heat cable manufacturers produce their product in both 120 volt, and then they've usually got a 208 to 277 volt product that will handle all three of those voltages in one cable. Now, they're typically designed around 240 volts. So when we talk about incoming voltage, when we apply less than 240 volt to a product that was engineered for 240 volt, you're going to get a little voltage deration there, okay? So now your 5 watt a foot cable might be putting out a little bit more like 4.2 watts a foot, you know, 4 watts a foot, so on and so forth. If we run 277 volt, obviously that's a little hotter, you know, it's running more juice, which is going to increase the output of your cable at base. So now your 5 watt a foot cable is really probably putting out more like 6.2 watts a foot versus 5. So as you can imagine, in most cases, you know, a little bit more is generally better than a little bit less. So, you know, 120 volt, 240 volt, 277 volt are all like fun voltages for us to design heat trace systems with, because we know you're going to get definitely the output that you need for that application. All we do with 208 volt is just compensate it with a slightly higher wattage output cable to make up for it. So to talk about the life expectancies, you know, and things like that, I mean, typically your better grade commercial and industrial based heat trace cables, you could expect to get a good, you know, 15 to 20 years out of them. You know, this is the type of industry where, again, you know, I know it's kind of a corny saying and cliche, but you do get what you pay for. You know, generally the premium manufacturers are going to have a better grade, you know, content to their irradiated carbon. So, you know, you can usually count a little bit more on that life expectancy. But one thing to understand is that heat cable is going to diminish its wattage output over time. And by that, I mean, you know, if you took a 5 watt a foot cable on day one, yeah, and by the time you got to, you know, say 10, 12 years into that process, you might be putting out 4 to 4.5 watts a foot on that cable instead of 5, maybe even down to 3. They can be tested and you can figure that out, but it will diminish over time. It doesn't just basically up and quit one day unless it was severed. Something else to note on these particular cables is that, yeah, stock voltages, 120 to 277 volt, typically always in stock. Anything beyond 277 volts is going to be something that would be a custom. You know, and then basically, if you ever want to figure out, you know, what the circuit length that you can go to maximum is you just need to know what the maximum wattage value per foot on that cable is going to be. And simply you can multiply that by how many feet of cable you want to put on the circuit, divide it out by your voltage, and that'll tell you how many amps you've got on that circuit, okay? All right, so constant wattage cables, that was the lengthiest one right there. So if you made it through that one, the rest of this should be cruising here. So constant wattage cables are exactly what they say they are. They are going to put out a consistent wattage per foot. There is no fluctuation in terms of you know, roller coastering effect where I've got to worry about computing out what the maximum wattage per foot is. This is very easy. I mean, if we're using an 8 watt a foot cable, you can simply do 8 times, you know, whatever, 500 feet divided by your voltage, and there's your amperage draw. Okay, so much easier to figure out your circuits. These cables, however, because they don't have a self-regulating property to them, is that they are going to heat and heat and heat until they're told to turn off. So these cables have a higher temperature threshold. I mean, these can perform up to about 320 F. You know, 390 F typically on maximum exposure temperature. As you can see, they can also, go from 120 up to 480 volt range. Basically, it's a very versatile cable. However, you do not want to use this one against anything PVC based because, again, there's nothing there to back off that heat, and eventually you will probably run into some problems with it either embedding into the skin of a PVC based pipe. Certainly we wouldn't want to see it melt through, but that's exactly why we don't typically recommend anything with constant wattage on PVC based materials. All right, so taking a look at the anatomy of this particular cable, again, you've got two 16-gauge bus wires, your primary over jackets over the buses. What makes this one a little bit different is you can see that resistance wire there. Now, that resistance wire is typically a 37-gauge nichrome wire, which I personally think is a little bit fascinating that you can pump 480 volt through a 37-gauge wire and that thing will last you 15 to 20 years. But, again, the tighter the winds on that resistance wire, the higher heat output you get. Or I should say, the less spacing in between each of those winds will ramp up the heat. If you see them, further apart, you can usually tell it's a lower wattage output cable, but obviously when in doubt, just look at the stencil on the side of the cable itself to get identification on watt per foot. And of course, you got a primary over jacket, tin copper over braid, and then, usually for industrial applications, again, like a UV resistant Teflon coated jacket. So when we look at the advantages of a constant wattage cable, these are 120 to 480 volt, which is great. They can handle 480 on a regular basis. You don't have that startup current inrush issue. These can easily be cut to length out in the field. One thing to note is, in the construction of this cable is that there's a node about every 2 feet. So when you cut one of these cables, go and terminate it out in the field, is that, you're going to be, if you cut, say, precisely in between 2 nodes, and those nodes are 2 feet apart, you're going to have no heat output if you cut it right in the middle between them for 1 foot of that newly terminated cable lead. Once you get beyond the node, you're creating resistance again, and the rest of that cable length will heat. So it's not really a bad thing. Okay, I mean, it's really nothing to look at as a negative per se. Okay. Yeah, the biggest thing about this as far as a negative is, again, you can't let it touch against itself. And this mineral insulated cable is very similar to constant wattage cable and exactly how it behaves. This stuff we have to take a little extra consideration because this cable is not a flexible jacketed cable. This is actually a metal sheath cable. And when we look at it in terms of industrial application, it's typically a stainless steel jacketing on the cable itself. So you can only imagine how sometimes inflexible these can be, to try and wrap around a pipe, or I should say, put around a radius bend. The nice thing about these MI cables, they are very robustly built as a metal jacketed product. These things also have to be hydrostatically dunk tested before they can even leave as part of their UL listing. So it gives it, kind of a different, it's really the most engineered of the heat cables, we could say. This product has to be made specifically to length. It's not something that you could really splice onto out in the field without, you couldn't just add, say, 10 or 15 feet of this because, hey, I'm a little bit short. This cable gets manufactured and welded, to its specific length and output. So some of the things that, really give this cable, some unique ability is its ability to, go up to 600 volt range. Its temperature tolerance is extremely high as well. I mean, these things can actually take temperatures of up to, 11 to 1400. Some of you folks, I'm sure, are probably familiar with MI cable used for fire pump suppression systems, to supply power to those critical pumps. And it's because of their temperature resilience. There are 2 different types of MI cables. There's one that delivers power. This is the one that creates heat. And the only difference really between them is the fact that this cable has a resistance wire integrated into its construction to create that heat. So there's a couple different kinds. We use single conductor and two conductor. And for this conversation, we're really just going to talk about two conductor because for an industrial application, it's really the only way to go. By two conductor, you can see this graphic here and how these are constructed. You know, that you've got two cores in there wrapped with magnesium oxide powder, and then either a copper or a stainless jacketing, you know, and then an HDPE over jacket. Now, in the industrial application, I would expect to see a whole lot more stainless versus copper. And that's really because of, again, corrosion resistance. This type of cable, the reason why it made the presentation is because, you know, whenever you've got an application where you're talking about, hey, I really not like to have to service that pipe again or do that pipe run for another 30 years or more, this is a great product for that. It really is kind of more like a one and done type of an application with this product. So, you know, its advantages are that, yes, you know, we can actually engineer this thing for temperature output. We can, you know, have this cable perform anywhere from, you know, call it 5-6 watts a foot all the way up to, you know, 30 watts a foot, 40 watts a foot. I mean, as high as we can go, I think is about 80 watts per foot. So that is some serious heat. You know, and I haven't run into an application yet where I had to get that hot, but, you know, it's nice to know that we do have a product that if we had to, we can get there. The circuit lengths are predictable because it acts just like a constant wattage cable does. Very rugged stuff, but again, it's a beast to work with. You know, it's not easy to bend this stuff around 90-degree, you know, pipe radius, elbows. You know, this isn't the type of thing that you're gonna have an easy time wrapping around a pump housing, let's say, and getting it to actually adhere right to the surface-to-surface contact you're looking for. It can be repaired. It's not impossible, but it would take rebrazing, rewelding. You actually have to re-weld the resistance wire to get this cable back in motion here. But big thing is, again, can't let this thing touch against itself. That pretty much wraps up our familiarity with the heat cables themselves. So let's talk a little bit about these applications. And when we talk about things like freeze protection, okay, everybody kind of knows exactly what that is. And you know, there's a lot of different kinds of freeze protection. Again, it doesn't always have to be water. You know, certain chemicals freeze at higher temperatures, greases, you know, so on and so forth. The nice thing about freeze protection is that a lot of times you don't have to be so exact. You know, this isn't like making sure that you're maintaining within a couple of degrees to get a process from point A to point B. So there's more forgiveness when designing these systems. So, you know, typically, you know, when we're doing something for freeze protection like water, here in upstate New York, we use a temperature range of say 40 degrees down to -20, giving us roughly a 60-degree delta T. Okay. We've done several where it's, you know, say 40 degrees down to -40. So it's a very predictable temperature variance that we're designing for. And then when you've got process temperature maintenance, you know, this is really about being exact. This is about being precise. And, you know, there's going to be, you know, obviously these factors of how much heat loss we have per foot on that pipe. And whether you figure that out in BTU or wattage, we do it in wattage, we can convert that. But we want to make sure that we try to keep our cables on process temp, you know, kind of as close to what the actual watt loss is off of it, you know, so that we don't disrupt the process or affect it adversely in any way, shape, or form. Remember, I told you early on in this presentation that the intent of the cable is not to heat what is inside of the pipe. And the only time that that actually can happen in most cases is if the heat trace system is still running and the fluid inside of your pipe stops. Okay, so as long as there's flow going through that pipe, typically you're not adding heat to anything that's inside of it. But I can't say that, yeah, if that was sitting stagnant in a pipe for an hour and your heat trace cable was running for that hour, that you wouldn't add heat to it. Okay. But basically what we're doing with this particular application, when you think about it in terms of design, is that, you know, it's what's the fluid leaving the tank at? What do we need to maintain before it gets to the nozzle of the sprayer it's going to, or the filling machine, or whatever it is that you're processing in that plant? It's what's the temperature it needs to be at by the time it hits point B. So, you know, again, you know, just a simple example that we did in the text of this slide, if you had 150-degree fluid leaving a tank and it's 60-degree ambient temperature inside of your plant, you know, you're now basing this off a 90-degree delta T. okay? All right. So when we talk a little bit more about some of these process temperature maintenance, sometimes not always about, just sending a food product through a pipe, be it liquefied chocolate, syrups, who knows, chemicals. This also applies to things like your COP, or CIP, cleaning processes, things like that, where you've got to have high temp water to wash down kettles, things like that. And hey, it's got to be 140 degrees or it's got to be 120 degrees. We also, see process temperature maintenance on condensate return systems. And it's a great way to effectively save energy by not letting your condensate cool off from, say, 180 degrees down to 140 degrees, and then reintroduce it into your boiler, because that's just that much more gas. Obviously, you're burning to twist that back up again, for 40-degree temperature rise. So, bringing them back on condensate return lines, often pays for itself pretty quickly. So if we look at a sample design here for a process application, okay, just try to draw a simple graphic here and a couple of products that you might see for a single circuit type of application here. So if we look at the process, at 140 degrees, leaving the tank's got to stay at 140, and you've got 150 feet to the next stop or wherever that fluid's being delivered at that point. Here's some of our criteria on the spec, right? Schedule 40 pipe, 2-inch diameter, 1-inch foam insulation, 240 volt power. So basically what I'm trying to do is walk you through this calc a little bit here. And that, if I've got an 80-degree delta T, okay, my insulation factor, we have a reference that we basically use to give us a factor based on just, generic insulation. And on that 2-inch pipe of how quickly it's losing heat, and basically determine this particular application, you've got about a 5.5 watt per foot loss on the pipe itself. So the recommendation in this type of process is we never want to be underneath that 5.5, or obviously, we could alter the process some, but, we can be a little bit above. We don't want to be double it. But a 6 to 8 watt a foot self-regulating cable is a great way to go for this type of an application, because again, my minimum output on that heat trace cable is going to be 6 watts a foot, and it really isn't going to go much below that, okay, but it is capable of getting down around, say, 5 watts a foot, and I can go up from there. So having that self-regulating cable there kind of ensures the fact that I maintain that balance. A constant wattage cable will do the same thing. Okay, the difference is that, again, the constant wattage cable usually runs a little bit hotter. It doesn't back itself down with the product itself. It does it through its controls. So again, that's just more of a judgment call on, either I've got a fluid inside of this pipe that I could coke if it gets a little too warm inside of there, or congeal it, versus it doesn't really matter. So you can see the load calcs down there in the bottom center. Again, 150 feet times 22 watts a foot, which is what the maximum an 8 watt a foot self-regulating cable can put out. If you can believe it, it can get as high as 22 watts a foot. So what I did was take my 150 times 22 and came up with 3,300 watts divided by 240, and you're at 13.75 amps on that circuit. So the single circuit controller that I have on there is capable of handling 40 amps on a circuit, and I can bring power right into the back of that thermostat. So I'm going to run a number 10, let's say, out to my thermostat, and come right out of the thermostat box with the heat cable on the pipe, and away we go. All right, so to talk about the control sum, again, excuse me, this is a segment that we could spend a lot of time on, but we're going to condense this thing, kind of keep it easy for you here today. So, as with most products these days, there are many tiers of controls that you can kind of get into, and it's really about choosing what's the right one for your application. So on the high end of things, we've got fully integrated heat trace panels that are breaker loaded. These things are, you can almost look at them like they're their own separate load banks. And that's the nice benefit to them, is that this is a fully integrated panel that's going to have breakers in it, contactors in it, GFI protection in it, HMI touchscreen, so you can access information that goes far and away beyond what standard mechanical based controls are going to give you. You can put alarm options into these things. You can tie circuits together We call it circuit mapping, where if, let's say you had 24 circuits out there feeding a decent sized tank farm or something, and maybe a third of your circuits are all 2-inch pipes. They're all carrying the same fluid through it, and if and literally you could put all 6 of those or 8 of those pipes together into its own segment, so that when that temperature threshold is hit, it kicks them all on instead of one at a time. But these panels, ultimately what I'm trying to tell you is you have all the versatility that you could want in one of these fully integrated panels. Now, the nice part of this too is that from the labor side of things is if this is a 200 amp panel, you just need to bring in a 200 amp feed, and this thing will distribute all the power through it. When we use something like a contactor relay panel, now you're coming out of a electrical distribution panel with, say, 6 30 amp 2-pole breakers, and you need to bring a conduit from each of those breakers to each of the circuits on the contactor relay panel. So again, your labor units go up a bit, but the cost of the equipment goes down. So that's the yin and yang trade-off that we're going to be talking about a little bit in this segment. In the bottom right-hand corner, we've got an example of basically like a digital 1-2 circuit type of controller there, where these give you a lot of the features and benefits of these larger fully integrated panels, with the exception of the breakers. You're not going to find breaker integration usually in these smaller panels, but they will handle the GFI code requirement. So again, you can work off a standard 30 amp 2-pole breaker out of your main panel, let's say. But the nice thing about these smaller 2-circuit panels is that, again, they're much more affordable. They're small and compact. You can put them into, again, pretty crowded situations, and glean a lot of information off them too. I mean, the nice thing about these automated panels is that typically if there's ever a fault, it tells you what it is, okay? And you can also get remote indication back to a BMS system, so on and so forth. So again, these are usually a pretty good option from the standpoint of it cuts the labor figure down. The downside to the high-end panel is that usually they're a bit more finicky when it comes to power quality, and things of that nature from within the plant. When we talk about contactor relay panels, we touched on it just a second ago. These are very affordable, usually a standard bearer on a lot of systems because of the fact that they're pretty low cost, but your labor units go up, okay? You've got to bring over each circuit to the contactor relay panel. Now, the contactor relays can also take care of your GFI code requirement. They will need a signal to close the contactor on them. So generally with a contactor relay panel, you are going to have a controller and a temperature sensor with that, depending on who the manufacturer is. Now, there's a couple of different ways when you talk about the sensors. Do we want to do something with ambient sensing, or do you want to do it with line sensing? Okay, now ambient sensing is just saying, hey, I'm taking air temperature, and when my air temperature hits 40 degrees or below, I want this thing to close all my contacts, allow power to get to my heat cables, and my system's running. Whereas when we talk about taking the skin temperature using an RTD, a thermocouple, something of that nature, is that we're actually taking the temperature right on the skin of the pipe underneath the insulation itself, which is going to be a lot more accurate to what the conditions the pipe is seeing is. So, again, even though the outdoor temperature may have gotten down to 25 degrees, a couple of weeks ago or whatever the case may be, it didn't stay down there for very long. So what was in the pipe or the skin of the pipe may not cool down to a point, to where the heat trace really needed to be kicked on. So, when you look at skin temperature, we like that because it's a lot more accurate and it's more efficient for your system overall, okay? All right, so single circuit controls, these are usually affordable, easy. When you're talking about smaller pipe runs, I mean, it makes all the sense in the world. Again, when you're going to put 30 feet of heat trace cable on, a number 6 oil line. I don't know who's using number 6 oil anymore, but I mean, you don't need a $2,500 digital controller, for 50 foot of heat trace cable. So again, single circuit controls are very popular. They definitely have their place in these applications. And again, it's kind of whatever you're willing to invest on it. I mean, the more you pay, the more capability you generally get. I mean, we've got stuff that are bimetal, bulb and capillary thermostats, like you can see in that picture to your right there, that are non-indicating. I mean, that's, those things have been around for 50 years. So they still work. They just generally have a plus minus temperature accuracy of 3 to 5 degrees. When we look at something digital with an RTD or a thermocouple on it, we're usually plus minus within a degree. So again, if that matters, I'd go with the higher end control. The other thing is too, is with the digital ones, generally you can jump off of an alarm contact inside of there. So if you do need to send indication someplace, you can do it. So that's another benefit to going with something that's a little bit more advanced on the single circuit side of things as well. So pretty neat though that, again, these little guys, they can usually all handle line voltage from 120 to 277. Some of them have GFI capability, some don't, but most all of them can handle up to 40 amp load. All right, so system designing. When we talk about system design basics, there's some minimum information that you definitely have to acquire before we can kind of even figure out where to dial in, the power or the output of that heat cable. And, really it all comes down to, what voltages do you have available? How much room can you, how much amperage can you pull out of that panel, let's say, right? If you've already got a panel that's already 70% to capacity, those are the things we need to think about before putting together a heat trace system with, 6 circuits on it. So, if anything, pretty basic, pipe diameter, how much length are we talking about? What's the layout of it? How many vertical runs and radius bends do we have to worry about? Are there couplings? Are there valves? Things like that we have to think about. Adding a little bit more cable to this thing to make sure that we've got enough cable to do the job. If that's one thing that I can tell you installers and contractors hate, is running short on the heat cable run. And by the same token, we don't want to be grossly over. Most manufacturers usually shoot for about call it a 20% safety or fudge factor they might build into it. Personally, I'll just say on behalf of ourselves, we shoot for more like a 10. So regardless of the fact, we don't want you to have a whole bunch of cable overage. And if we do our diligence on the front side of these designs, generally, again, the materials really work themselves out to be quite accurate. And, but those are the considerations, right? We've also got, what's the insulation thickness we're going to put on that pipe? That's going to determine our watt losses per foot. And of course, what's our temp range? Can't really do anything until we know exactly what the objective is. And, I put in there in parentheses when I talk about freeze protect, usually not pressurized and then process, usually pressurized. More of a reminder to myself as we get into a little bit of this install segment of things as well. So I'm just going to touch on it for a quick second. When we put heat trace cable on a pipe, we strongly recommend using linear runs down the pipe. Okay, I know a lot of people think that this stuff gets spiral wrapped around the circumference of the pipe. When you think about that for a second, okay, to get your circumference or the length of what you would need to do whatever, 100-foot length of a 2-inch diameter pipe, you're taking that 2 inches times 3.14. So the long and short of it versus that linear run is that you're going to use a whole lot more cable trying to spiral wrap that thing around a pipe versus just taking one straight shot down the bottom half of that pipe, and it's going to be just as effective as spiral wrapping it would anyways. And here's why. If it's a non-pressurized situation, typically like freeze protection, your moisture, your water, your fluid, whatever's inside of that pipe, gravity is going to pull it to the lower half. So we want the heat trace cable on the lower half of the pipe. If it's a pressurized system, okay, now you've got fluid obviously from top to bottom inside of the pipe. Now, it doesn't really matter so much exactly where the cable is. I mean, obviously we'd like it on the lower half. We feel that's certainly a much more efficient way to do it. But just to clarify that point, so you knew, there were differences obviously between pressurized and non-pressurized systems. Some other things that we would strongly recommend is confirm your voltage site reading. Okay, I mean, we can all say, and read obviously that, hey, it's 208 coming out of this panel or it's 277 coming out of this panel, but what do we truly have there? Because especially when we're talking about 208 volt, is that we've got that voltage deration to consider. So again, if we're looking at engineering a job at 208 volt, and we know already that we're going to have to deal with being handicapped, you could say a little bit on that one, and then come to find out you're really only pulling 202 or 203 on that circuit, not 208, you got to compensate a little bit for that too. So that's why we try to dot that I, cross that T. You know, what other equipment is being fed from that same panel? You know, is it something like a big motor where you're going to get voltage drops, you know, things like that? I mean, those are all considerations that kind of come into this thing. You know, are there any surge protection or power conditioning devices helping to, you know, to mitigate these transient events that could screw up the microprocessor in your heat trace controller and throw a fault? These are all things that, you know, we try to get on the front side of it so that we can make sure it's going to be a clean, you know, design and install. The third point is actually pretty neat in that when we talk about justification for adding a redundancy, let's just use the example. I know this isn't so industrial per se, but I think everybody could relate to something like a grease trap coming out of a restaurant. So you got roughly 30, 40 feet of pipe that's going from a main drain, let's say, out to a waste tank, and it's buried underground. Here's a perfect example of making the comparison between what's it going to cost for me to grab a backhoe in 15 years, dig up the parking lot, open up that trench, expose the pipe, take off the heat trace cable and the insulation, put on a new line of, a 40 foot, mind you, 40 foot of heat trace cable on this thing, rewrap it with insulation, fill back in your hole and call it a day, right? The heat trace cable is going to cost you $1,500 bucks. The rest of the project's going to cost you 30 grand. So, you know, where we look for these types of applications is, again, where you know that over time replacing this is going to be a big headache. It's a great justification to think about having a primary heat trace line that is connected to power that would function and do exactly what its intent was to, but to also have a secondary line installed and then insulated over, okay, and we can leave those two cut pieces of cable at the end with end seals on them to protect them from moisture and over time, you know, damage or ingress, so that when the first cable eventually dies, let's say in 15 years, you can literally just hook up the new cable and you're back in business for another 15. Okay, so those are I think are really valuable to end users when somebody's trying to think forward into that type of a scenario where, again, we can kind of call it a day on this particular application for the next 30 years. So think about that when you're looking at your applications. And another big one is, hey, where are you going to pull power from to bring it out to your pipe trace system? So, you know, J boxes, you know, where are we going to put splice kits, things like that all matter. And it's going to determine, you know, some of those things like how much cable, you know, because here's a perfect example of it. You know, we look at a graphic of doing like a typical heat trace design like this. If you look on the far right of this slide where I've got down and back versus splice kit, okay, what I mean by that is when you come to one of these situations where you've got, say, a main header heading down the middle and we got our big yellow OS and Y valve there, and, you know, as we come down to that T where you can see it looks almost like a little heat exchanger or something in there, it says caution, you know, electrical heat in the graphic. Now there's two things you can do when you get to that T. Either you can put a splice box there, like we kind of did with that UMC, you can see in parentheses, and you can take a splice on your heat cable and push it up that line, or let's say that that's only 10, 15 feet of, you know, run coming off of that T. Most of the time it's going to save you a heck of a lot more time and money to just go up to the end of that run, come right back down it, not even put in the splice. I mean, to do an accurate heat trace splice is probably going to take you a good half hour. Plus you got the cost of the J box on top of that. Okay, and while we're talking about that J box, I would strongly recommend don't ever use an under insulation splice kits. Okay, you won't be able to find them again after the installation is over with. So, you know, anytime you have to do a splice on a pipe trace system, make sure that it is an above insulation splice kit. You can access it. You can get in there with a multimeter. You can test, you know, to verify if that particular splice was the bad one, things like that. So, you know, that part is critical. You know, but oftentimes an extra 15 feet of heat cable is a much better investment versus trying to pull off a acceptable splice plus the splice box and everything that kind of goes into that. I say that with a little bit of, let's say bias towards the fact that, again, you need to know in some respects, like you don't ever put a double run, even if you're low temp, uh, self-regulating cable on, say, a plastic PVC pipe. If it's a metal-based pipe, you can do that, and that's no big deal, okay? But I'm just going to back up for a second, give you a real-world scenario here. If this was a PVC system that we were tracing right now on this slide, if I'm using a 5 watt a foot cable because I'm losing, say, 4.2 watts a foot off of this system, and I take a 5 watt a foot cable, which is perfect, and head right down that PVC pipe and then double it back and, take it for another run down the other side of it. Now I'm at 10 watts a foot in an application where I only need 4.2. And once you throw an inch or an inch and a half of insulation on there, 10 watts a foot is going to be a lot of heat. So over time, it's nothing that may damage something immediately by any stretch, but over years of that kind of exposure, hours, things like that, where the system maybe stays on for, who knows, 5 hours, or something like that. Yeah, there's the potential for that cable to build up too much heat, despite the fact that it's self-regulating. Remember, it can't really go much below its output value. So there's only so far it can go down. So when we talk about going down and back, it is still pretty specific, but just again, something to kind of plant a seed in your head into saying, again, if you were doing a water main and you're going to have like 10 branch circuits coming off of that, you don't want to have 10 splice kits on your job if you can avoid it. Okay, now the installation success is more in the hands of the installer versus the product itself to make good terminations. So talking about things like, again, back to the bottom left-hand corner where we've got some little bullet points down there to consider, things like, compensating with additional cable for things like slacking valves. So again, if that valve has to be replaced down the road, all you have to do is basically remove the heat cable from it, unbolt your flanges, pop out the valve, pop in a new one. You could actually reattach and rerun the cable all over it, and you're back in business. The reason why I've got fiberglass tape in there is because that's the preferred way that we adhere the cable to the surface of the pipe itself. Fiberglass tape has a very high temperature tolerance to it. So, if you try to use something like duct tape or a standard tape, I don't even want to know what that would do to the adhesives and what kind of mess that would create. But yeah, needless to say, this stuff is very low profile. You're only talking about a quarter to half inch thick. And then you'd use it about every, call it, say 3 to 5 feet, put a wind around the pipe to keep it tight to it. Now, aluminum tape is a real good product to use to help dissipate some heat across the surface or the skin of the pipe. And that really comes into play when we're talking about like big diameter pipes, things like that, okay? And then of course, we've got things like lighted end seal kits, so you can, ensure that your system is running, even if it's a single circuit controller and you don't want to pay for, again, multi-$1,000 control panel to know whether or not your heat trace circuit is operating or it's not. So I know that we're starting to get a little closer to our time limit here. So I've got a couple of slides here where we're going to talk about some of these points. And then again, contact us down the road or send something to Ryan there in the email chat, because these are some pretty important points that we consider when we're looking at design layout and just some general rules of thumb that we've learned over the years from doing so many of these is, things like, again, metal pipes give you a lot more forgiveness versus something like PVC. So if I'm over, if I'm using an 8 watt a foot cable for a 5.5 watt a foot application, yeah, I got no problem there, because the metal will take it. In PVC, you got to kind of watch how much heat you're putting on it. The thicker the insulation, the less wattage cable you'll need. That's just basic logic, right? Many times the installation can get expensive. So, sometimes we see a little bit of a balancing act between, hey, what cable versus how much insulation. But know this is that, yeah, once you start getting up into an 1.5 inch, 2 inch insulation on that pipe, yeah, you're not losing a whole lot of heat. So it definitely helps the efficiency and being able to lower the output of the cable. Linear cable runs, we just touched on that, versus spiral wrapping. can pretty much tell you that you'll probably use about 2 to 3 times. You'll easily use twice as much and 3 times as much cable to spiral wrap versus a linear run. And then, we're looking at things like vertical downcomers, things like that, state of the outside of the radius bends, seems pretty logical. Obviously, that's the larger surface area of the pipe. It's got more length to it, and that's obviously where gravity is going to pull your fluid down to the outer portion of that pipe or the lower half of it anyways. So things like using aluminum tape with PVC pipes, that's a great idea. That helps dissipate that heat, helps reduce the potential threat of having a hot spot, or something where you could have a potential for melting. And the other thing that aluminum tape does really well is when we're talking about larger diameter pipes, like let's say something like a 12-inch pipe, be it steel, it really doesn't matter what the material of it is. It's that, your heat trace cable is really only going to be about, a 1/2 inch to 3/4 of an inch. And it's more like a 1/2 inch, about a 1/2 inch wide. So if you can imagine 3 1/2 inch wide runs down a 12-inch diameter pipe, again, you've got heat in an 1.5 inch footprint, and you've got 12 inches you got to cover. So we want to proportionally spread those runs across the bottom half of the pipe. Okay, so if you could imagine a clock face, and you've got to run at say 4 o'clock, 6 o'clock, and 8 o'clock is probably where you'd want to put those. And take some aluminum tape, cover them, and now you're spreading that heat across basically the whole lower half of the skin of that pipe, which is going to, definitely help out the efficiency of your system there. So we talked about above insulation splices and electrical connections. Less splicing is better. And another, tip that we would give you is always voltage check, after your splice connection to ensure the fact that you're getting proper current ampacity to the rest of that run. But that's exactly why we try to reduce the amount of splice connections, because, again, if the electrician just digs a little bit too far into that bus wire and cuts out a few of those strands, you're not going to carry as much current through that as you would if you never spliced it at all. So, when we talk about sizing our circuits, 30 amp 2-pole is typically the way we go. But again, it's a function of the math. If you don't have 30 amp 2-pole breakers in the facility that you're designing for, then we have to work within the confines of a 20 amp or whatever we're kind of given. Okay. When we talk about pipe sensing versus ambient, this is another one where, again, it's not that ambient is wrong by any stretch. We just feel that skin, pipe sensing is going to be more accurate. It's usually going to lead to your heat cable being on less than it would for an ambient system, which again, over time can matter. If we're letting these systems run flat out, I mean, voltage is essentially what winds up degrading the self-regulating carbon mastic, which gives you all that flexibility. So, over time, if we can keep some cycles off it, that's not a bad thing. It's not huge, it's not, but by the same token, it can make a difference. Really when it comes down to it is when you're talking about something that's just real simple, easy, something that's, again, kind of anybody can get in the game on, single circuit bulb and cap controller is, maybe a few $100, a couple $100. And the end seal, they're generally kind of on the more expensive end, but you're probably looking at $250 for a lit end seal or something too. But again, for around who knows, $500-800, you can be in the game with a heat trace run there, and as opposed to multiple thousands of dollars, let's say, to put in more advanced product. Okay, so. Really when it comes down to it also is, there's some factors within the facility itself also that could be limiters, like the age of the panel that you're tapping for power. Do they make breakers for that panel anymore? Can you even get GFI breakers for it? Because in a lot of these cases where, again, you can't get an upgraded GFI breaker, well, now's the time to consider using the control that's got GFI integration into it. Okay. Definitely do not pull power if you can avoid it from entrance panels that have big draws or fluctuations. And whenever you're using microprocessor-based controls, if you want to use the advanced controls, we'd strongly recommend putting in something like a surge protection device to mitigate any electrical interference that can come back through that circuit. And then of course we talked about basically what cables are designed around voltage-wise, and that 207 runs hotter with a 240, or I'm sorry, 277 runs hotter with 240 volt cable, and 208 runs cooler. Just a couple more slides here. I know that we're basically to our point here, but here's a couple of your insulation types, or common insulation types. Again, you need something. In most cases, I don't think you need to get anything exotic on there, but as long as you got at least an inch of insulation, that's what we shoot for, is an inch to an inch and a half. Will usually take care of you just fine in most of these applications. And once you start getting over an inch and a half, it starts getting pretty expensive anyways. And then when we talked about the installation tips really quick, linear runs versus spiral wrapping, when I was talking about 5 and 7 o'clock, hopefully this graphic on the right helps give you a little bit better depiction of what I meant there. As far as where to place the cables on the pipe itself. And you can see a nice example here of where this graphic has the temperature sensor, where it's at least several inches away, let's say, from where the heating cable is. Obviously, we don't want to get false reads, so do not locate your temperature sensor next to the heat cable itself, okay? And then, of course, we talked about some dissipation with, aluminum tape. And yes, every 4 inches, okay, on your pipe diameter would require another linear run. Okay, so 4-inch pipe, very common pipe size. We can do 1 run of heat trace cable on a 4-inch pipe, good. Once you get to 6 inches, 5, 6, 8, we would strongly recommend going to 2 runs on that pipe, because your surface area is increasing. You need to put multiple runs on there to ensure that the section of the pipe stays to the temperature you need it to, because 1 line won't do it. At a 1/2 inch thick, it's just not enough. So and the biggest thing when we're talking about with installation is Megger testing. Okay, basically every heat cable manufacturer is going to require that you use Megger testing for warranty purposes, but that's the easiest way to ensure the fact the cable wasn't damaged during installation. And for those of you folks that are not familiar with what a Megger tester is, similar to a multimeter, okay, but we're not checking current and voltage value. All we're checking actually is the insulation value of the jacketing on that cable. All right, so when we send a test charge through it, if there's a cut in that jacketing or a leak to ground, this device, this tool is going to show us that. And then before you spend a lot of money to insulate over the top of that pipe, we can address the issue versus, everything's on, you paid big money for ceramic insulation or something like that over the top of these pipes, you flip on your circuits and find out you got a fault on one of them, and if it was due to, again, just the cable was damaged because it got pulled across a burr, something to that extent. So, if the installer is measuring on a regular basis, he can easily uncover any sort of damage to that cable, before we get too far down the line. So, really when it comes down to it, is specifiers I would strongly recommend for you folks that, either integrate in startup and commissioning into the spec, an evaluation by, either the manufacturer's rep or the installers have to submit Megger readings, resistance readings, before, during, after on the project type of thing, to ensure that the cables were, installed correctly and that they're in proper working condition, to close out that portion of it, let's say. But, really when it comes down to it, very seldom do we see actual defects in the cable construction itself. Most of the time it's I don't mean to point a finger at anybody or disrespect, what our installers do out there on a daily basis. But unfortunately, it's the type of application where if you try to cut a corner, you're going to know about it. You're going to find out the hard way. So the summary, and just wrapping this thing up, and I appreciate you folks letting me go over by just a couple of minutes here, but heat cables are a very versatile product. Again, these have a lot of different applications to them. I won't get into all that, but again, it's pretty simple installation as well. They have a long service life expectation. They don't emit noise, they don't emit emissions. I mean, this is something that, again, can be used in tons of different applications. When we talk about it for process, I mean, obviously it's maintaining fluid temperatures, and some of these processes, I know, again, if throwing away a batch of product is $10,000 and the heat trace system, is $30,000, then, in my opinion, yeah, this thing is there to save you money. I mean, if you've thrown out more than 3 or 4 batches, you already paid for your system, right? So, obviously making sure that temperature maintenance in your process is got to be saving you money overall. And then, of course, freeze protection, we all know what happens there. So again, I want to thank you all very much for your time. We appreciate it. If there's any more information that you'd like, please contact us. We'd love it if you could visit our website. We've got a tremendous amount of information on there. Thank you very much all, and hope you all enjoy your weekend. Take care.